Okay, part 4, electrolytic cells. So the only difference between a galvanic cell and an electrolytic cell is that a galvanic cell is spontaneous. The electrolytic cell, we can force the reverse or non-spontaneous reaction to occur by hooking it up to an energy supply. In this case, it would be a battery. We're going to supply electrons to push the equilibria to the left. All right, so that energy source I said was the storage battery. Now, what people confuse with this is that even though it's the reverse reaction, we haven't reversed the physics. Oxidation still occurs at the anode. Reduction still occurs at the cathode. All right, so the difference here is we're running the reverse reaction. So when they say we're going to create a system that has M+, they mean some sort of metal cation in solution. And then X- is going to be some sort of anion, but it's oftentimes a spectator. It's usually chloride or something of that nature. All right, so notice that we don't have a salt bridge here. We don't have to. We're forcing the direction because the battery is supplying the power. So the battery is forcing electrons into the cathode while removing electrons from the anode. So there's no need to balance the charge because the charge is being balanced by the power of the battery. Now, at the cathode, you still have reduction. So this metal ion is becoming solid metal, and that's actually going to form on the electrode itself. And in our lab, we would measure how much of that metal forms after we hook it up to a battery for a certain amount of time. That I already said. And they define electrolysis here. We're going to run the reverse reaction by pumping in electrons at the cathode and using them for reduction, and then removing them at the anode, causing oxidation. So a couple things they like to have you calculate: the amount of products formed from the process, the amount of energy required to run the process. So I said, go back to the first part of the presentation where I said, look, there's some formulas in there that are pretty helpful. For instance, if we're looking at the amount of products formed, then we can get the moles of electrons transferred from the balance reaction, and from there we can figure out the coulombs of charge. And a coulomb is equal to an amp second. So what they'll do is they'll tell you the amperage of the battery and how long you're running it. From there we get the coulombic charge. That we can translate into moles of our product, and then we can get grams. Second thing that I like to ask is how much total energy is involved. So we had said that voltage is joules per coulomb. So we can solve this for joules, and energy is actually a coulomb volt. All right, so first problem, we're going to silver plate something, which means we're going to take a solution of silver nitrate, and we're going to run a silver electrode, or any sort of metal electrode, actually, that doesn't react with this silver nitrate, and we're going to cover it with a layer of silver. We're going to do that by pumping in a current of 2.60 amps in 1 hour. All right, so this is a pretty easy calculation, as long as you remember that again, voltage is joules per coulomb. So therefore, joules per coulomb, and we said that coulombs were an amp second. So I'm going to use this second relationship. Coulombs equals an amp second. So I'm going to calculate the number of coulombs of charge force. They tell you the amperage. And we're going to multiply by the seconds. Now it's 1 hour. So we could work out that conversion, but 1 hour is 3,600 seconds. And when we do that, we get me get my calculator. 2.6 times 3600, I get 9,360 coulombs. I'm going to convert that to moles of electrons. So 9,360 coulombs times 1 Faraday. Oh my goodness gracious, not times 1 Faraday. Sorry. Use Faraday's constant, 96,500 coulombs per 1 mole of electrons. Now, in the balanced equation, it was silver ions plus 1 mole of electrons produces silver. So I know that for every 1 mole of electrons, I get 1 mole of silver. And from there, I can calculate the grams of silver. 1 mole of silver. I look up silver, it's 107.868, I think. Yes, grams. And hopefully when I do that, I get 10.5. So 9,360 divided by 96,500 times 107.868, and I get 10.4626, so 10.5. Okay. There are 2 commercial cells that they want you to understand the processes of. The first one is called a Brine Solution. And Brine Solution, what they're doing is they're using seawater and they're hooking it up to a battery to create, well, this says OH minus, but really the whole thing is to create sodium hydroxide, which is a very important material in catalyzing industrial processes. So it's our process for creating OH minus solution. So the voltage for this is high, and it makes sense because look at the reverse reaction. You have OH minus and hydrogen becoming water, that's a strong driving force, and chlorine becoming chloride, that's a strong driving force. When you add them together, the reverse reaction would tend to be spontaneous, but we can create this forward reaction by hooking our seawater sample up to a battery, as long as we run the battery at least 2.188 volts. Okay, so how much energy is required to form 1 mole of chlorine gas from a brine solution? Okay. Let's see what we got. We have our reaction, and we just have to remember that voltage is joules per coulomb. So therefore, joules are coulomb volts. And it's a matter of coming up with the number of coulombs of electrons. Now they're telling us what to start with, 1 mole of chlorine. That's what we're trying to produce. And I know that for every 1 mole of chlorine, I am going to transfer 2 moles of electrons. 1 mole per chlorine atom. So we're going from a charge of chlorine equaling 0 to chloride equaling -1. That's 1 mole of electrons, but there's 2 atoms, so we multiply it by 2. So for each chlorine molecule, there's 2 moles of electrons transferred. Also know that for every 1 mole of electrons transferred, we have 96,500 coulombs. So this comes out to be 193,000, yes. 193,000 coulombs. So now I can just substitute into that equation, energy is equal to a coulomb volt. So we have 193,000 coulombs times a voltage of 2.188 joules per coulomb. That's what a volt is. And I get 422,284 which we can convert to kilojoules. Again, those relationships that we talked about in part 1 come in handy in these sort of calculations. The second commercial battery that they want to talk about is the lead battery that's used for car engines. And in that, we have alternating lead plates in a solution of sulfuric acid, and that creates the oxidation of lead at the anode and the reduction of lead from lead 4 plus down to lead 2 plus at the cathode. Now, the problem with this is one of the products of this is the lead sulfate solid. And this lead sulfate solid tends to accumulate on the plates of the batteries, and as it accumulates, eventually the solids on the plates will touch and the car battery will go dead because it short circuits. That's one issue with the battery. The second issue is that as you discharge the battery, you're turning acid into water. So the concentration of the sulfuric acid decreases. You have less on your reactant side, more product being produced, which shifts the position of the equilibria. So as you run the battery, you're moving towards a position where you're going to get a voltage of 0. Now, the car has what's called an alternator. So it has an electromagnet in it that spins. It's hooked up to the serpentine belt of the car. So as the tires go around, it spins the electromagnet, which creates current, which recharges the battery as you're using it. The issue is you can't push the equilibria all the way back to what it was when the lead storage battery was first made. So eventually, even if you didn't have this salt bridge that's created by the lead sulfate between the plates, you would still wind up with a dead battery because you can't completely reverse the process. Anyway, all right, so those are the two storage batteries they want you to know. In the last videos, what I'm going to do is take a look at 8 practice problems. I'll split it up into 2 videos of 4 problems each, and that will be the last chapter of AP Chemistry.